Um, so we are going to be doing base nets, continuing from where we left off last class. And it's going to be a very useful, important class and making sense of a lot of things in your life, including this course. So that's basically what we're going to do. The midterm 2 would be next class, as you all know, and as I said, it is going to be, at least compared to the previous exam, which you will see. Since you people are into cheat sheets, you can get a cheat sheet. You get up by 11, both sides. You don't really have to do miniature painting. Although if you need help, one of the TAs can help you. She's very good at it. And then the calculators are allowed. Again, we are trying not to require calculators in most of the questions. There may be one or two where there may be some decimal arithmetic. But so calculators are allowed. We would assume that the calculators are required and allowed. But you are not allowed to use cell phones unless you if you have to use cell phones, you have to sit somewhere in the front so that the TAs can see if you are depending on the world's wisdom to answer your questions. Okay. Seriously, I think you should just we keep saying that you need a calculator. So get the calculators that you have put away in your drawers or something. Okay. That's basically what you're going to do. And so nothing connected to the web, nothing, no cell phones. And if you have an emergency that you don't have any other kind of calculator, you have to let the TAs know beforehand, and you should be sitting in the front so they can keep an eye on you. Okay. Especially if you're checking out CNN or Sports Illustrated or something, wasting time, they'll let you get all the class. Okay, that's about that. Any questions on the midterm?
Does the cheat sheet have to be handwritten?
I don't care. Do we care? I say my entire life I didn't do a cheat sheet. So I just understood this concept only after coming here. So I have no
I
idea.
think it won't matter if we're going to do like the tiny print like I do.
Okay. Well, she said that. I didn't say that. But anyway, yeah, go ahead. I think it's fine with us, essentially. But if you wind up getting like a microscope to look at your cheat sheet, there may be questions. Yeah, it's fine with me if you print it. I think it's okay. I think the whole point of cheat sheet should be that in writing it, you're remembering things. Beyond that, I don't know if there's any point. Okay. And that, if you're like one of those people who are very stressed about remembering anything, sure enough, you will be old and you won't remember a thing, but right now, if you're still stressed about remembering stuff, cheat sheet myself. Any other questions? Okay, so I myself will be there. Actually, that's Kashan, Taiwan, and I'm told that if you walk in from the dragon's mouth and come out of the tiger's mouth, then all the bad luck will be converted into good luck. So I might do it for you as a prayer. Okay. So, seriously, actually, I would be giving a talk on Friday morning, which will be like around the same time you might be taking this exam on Thursday because it's 15 hours time difference. Anybody from Taiwan? What sort of class am I running? Nobody from Taiwan. Okay. So anyway, that's the story about that. One other thing before I forget, I just got this mail. Remember this guy? Like the guy who does vandalism to our walls? So he's giving a talk on, so he's going to be here, obviously. He's actually on our faculty now. He spends 6 months here, or something of that kind, and he'll be here for the spring semester. And so on November 22nd, apparently he's going to give a talk on 10 ideas in approximate, so he'll say reinforcement learning here just to get you there, but as soon as you go in, he'll say approximate dynamic programming. But you should know not to leave. because approximate dynamic programming is reinforcement learning. So you might be interested in going there if you got interested in reinforcement learning. And he's also teaching a course just on reinforcement learning, mostly for PhD students in next semester. But if some of you are very, very interested, I can put in a word and maybe you can take the course. So he'll also tell you about the course that he's teaching. He taught that once here already, and it was only taught for the PhD students. Anyway, he's a very smart guy and certainly what we're doing. Okay. So that's about the announcements. So let's get started. There is, I don't know how I got this, just the right day, because somebody as I was standing outside, receiving outside, this girl was like so happy and she was walking by saying, finally Seattle weather. I don't understand why. Come here. I was happy with Phoenix weather finally, but now it's become Seattle weather. Anyway, so these things you may not normally know what these are, but there is something called rain that sometimes falls. And there is, civilizations have found some sort of a theory and correlations between these things. Cloudiness and sprinklers and rain and wet grass. Okay. By the way, remember I used the cloudy, sprinkler, wet grass to yell at certainty factors. Remember, because I said wet grass might imply it was raining. Raining might imply wet grass. And so you can get into circular reasoning. Okay? Probabilistic reasoning will ensure that you will never get into circular reasoning. Basically, you imagine you're going to, if you remember what I said last time, by the way, is this better or putting the right arm is better? Does it make a difference? Okay, so if you remember what I said last time, Bayes networks are best seen as representing the joint probability distribution. Okay? In particular, you can think of, if joint probability distribution was to be a big number, you can imagine that the Bayes networks are factorizing them into small numbers such that when you multiply them, you get the big number. Okay? That's why I said factorization. In fact, today I'll show you what I specifically mean by factorization. Factorization essentially will wind up being conditional probability tables at the various nodes. You can multiply them, except it's not a matrix multiplication. It turns out to be this crazy kind of multiplication called joint multiplication. How many of you have taken databases? You know relational joins. Okay, so you essentially take two relational tables, essentially join them, and then whichever rows join, you multiply those numbers. That's how you get factors to be multiplied. So each factor is a little table, and you multiply all the tables to get a big table. The big table is the joint probability distribution. Okay? And ultimately, I kind of made a huge point about the fact last time that joint probability distribution is your ground truth in probabilistic reasoning. Just like the truth tables are the ground truth for propositional logic. Everything can eventually make sense of from truth tables, right? Everything else, what you did the rest of logic class is how to do entailment faster. But the semantics came from truth tables. Similarly, the semantics for probabilistic reasoning finally come from joint distributions. Okay? So keep that in mind, and we'll basically push this like multiple times into your heads. But so towards the end of last class, we looked at Bayes nets, and we looked at how to specify them. So here is a Bayes net. This also tells me if anybody is actually, this is one of these strange things that we got into when there was a poll as to whether people wanted an extended period. There was 70% of the people who wanted it, but 80% leave every time. And YouTube, apparently, you guys have found some way of doing anonymous viewing on YouTube, because the counts on my videos, even for that last part, don't seem to go above 7 or something. So I'm just assuming that people have found a nice way of learning stuff without actually seeing anything. So we'll figure it out today. So here is a Bayes network. We looked at a different one last time. is a Bayes network. So how many probability, what probabilities do I need to specify this network? Yes?
Probability of it being sprinkler or rain.
No, let's start total. So cloudy, for what, cloudy, what do I need to give? Probability of cloudy, true.
Yeah.
Then 1 minus that will be probability of cloudy, false. Okay? How about here? What do I need? Remember, the basic thing was in Bayes networks, for every node, you need to provide conditional probability distribution given its immediate parents. Right? That was the deal. So for sprinkler, I need to provide what is the probability that sprinkler is true given cloudy and given not cloudy. Right? And similarly for rain, I need to provide what is the probability that rain will be true given cloudy, given not cloudy. And here for wet grass, it has two immediate parents. Right? And so you will wind up giving wet grass, but then sprinkler rain, sprinkler not rain, not sprinkler rain, not sprinkler not rain. Again, I'm basically doing this because I'm assuming all these variables are Boolean variables. There is really, in fact, one of the interesting things we'll find out is the semantics of Bayes networks that you will understand in this class have nothing to do with whether the variables are Boolean, whether the variables are multi-value, or whether even the variables are continuous value. But it makes a lot more sense to think in terms of Boolean because that sort of makes us connect it very nicely to probabilistic, to logical reasoning. You see what I'm saying? And that's the way of putting it. But in fact, I will show you a couple of examples of continuous Bayes networks too. And the idea of the semantics basically remains the same there too. So even there, had this been a continuous variable, you need to provide its continuous probability distribution given the parent's values. So in fact, you can have, for variables, a network can be mixed. It can have Boolean, it can have multi-valued, as well as continuous variables. So the expressiveness is there, a lot of expressiveness. Okay, and so all you're trying to find out here is to give the conditional probability distribution. So what a really conditional probability distribution is WG and not WG, because for WG, it only can take two values. So the giving distribution for WG, wet grass, is what is the probability when it is true, what's the probability when it is false. Since there are only two values, if I just give one of them, probability for wet grass, I know not wet grass. Had it been the case that wet grass is a 15-valued variable, then you need to give it probabilities until at least the 14th value, because the 15th value will be 1 minus all these other numbers. If this was a continuous variable, you really have to provide a continuous probability distribution. In fact, in the case of continuous distributions, there are all sorts of interesting things. How many of you have taken probability distribution probability classes? And you remember the continuous densities and etc. You know, discrete and continuous are very close, but obviously continuous, wherever you see in the rest of the class a summation, think integration if you are into continuous. Okay, that's basic idea. Okay, that's that. So how many numbers did I need to give? Remember that I don't actually need to give this because I can get them. Why give numbers that can be computed? By arithmetic. So how many numbers did you have to give total?
9.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 numbers. How many numbers would you need to specify the joint distribution fully? If you are trying to specify the joint distribution instead of giving the CPTs, how many numbers do you need? 2 power 4 or 2 power 4 minus 1. Okay? Except that the minus 1 is at the base, not at the superscript. Remember that, okay? So it's basically instead of 2 power 4 minus 1 equal to 15 numbers. What if you have a, so first of all, let's look at this. Does this kind of make sense to you? This, imagine you kind of understand how cloud and wet grass and rain kind of work. Do you sort of see that cloud is sort of going to affect sprinkler and rain, and sprinkler is going to affect wet grass and rain? You sort of kind of see that. Okay, now here's the interesting thing. Imagine you are living in a world where you would like to hope that everything is independent of everything. So then what would the network be like? It would be, the happy network would be like this: cloudy, sprinkler, rain, wet grass. No links. This tells you, so when you drew these arrows, you basically in essence said what depends on what. We'll actually provide the theory behind it. We'll specifically try to say that Bayes networks are a compact way of representing conditional independence assertions. Conditional independence assertions. And so if you happen to believe that in your world certain things are conditionally independent given certain other things, okay, then you drew that network to kind of compactly represent those conditional independence assertions. If you, and the worst case scenario is if you believe everything is independent of everything, without any conditions even being given, this is the network that you would draw. If you drew this network, so this is called the topology of the network. Here is a topology, here is a topology. If I drew this network, what is the number of numbers I need to write for it? 4, just 4 instead of 9. You see what I'm saying? Suppose I am not that greedy, I somehow want to write something like this. Well, cloudy causes sprinkler, causes rain, causes wet grass. This is my theory. And by the way, whenever I say cause in today's class, think correlation. Because I'll make a huge deal about the fact that Bayes network have nothing to do with causation. We just like to say causation. It doesn't have to be necessarily causation. That's the point. Okay? So if you happen to know the world, then you may have some theory of causation. If you don't, and you're learning these networks from data, your computer has no theory of causation. It doesn't know what caused what. Do you see what I'm saying? So, in fact, one of the things that will happen in today's class is, I will take something like cloudy, sprinkler, rain, and wet grass, and I would either try to do what's called a knowledge engineering approach, where I happen to know the domain, so I will give you the topology. And then if I give you the topology, you can maybe either learn the numbers from data or ask the experts for the numbers too. The other is the middle ground. So basically I can start with the topology and also ask for the numbers. That is the most knowledge intensive way. That means you're asking somebody for everything. The middle will be, let the experts give me the topology, I will get the numbers from the data. That's quite cheap. The hardest would be, I will try to find the topology as well as the numbers that correspond to the underlying probability distribution of this data. When you do that, the arcs that you put in don't have to have anything to do with causation. In general, Bayes networks don't require anything to be causal. When you do this, maybe you kind of knew what causes what, which is why you do cloudy, then sprinkler, then rain, and then both of them causing vectors. Maybe because that you knew this is how things work in the world. That's not obvious at all from data, unless you do experiments, unless you do interventions. Like for example, if you dry the grass, will the rain stop falling? You see what? That's called an intervention experiment. Okay? If you, basically, if you sort of clean your nose, will your flu go away? Or if your flu goes away, will your nose stop running? These are the experiments you've done in your life. That's why you know what is causing what. In social studies, we are all full of fake theories of causation. For example, is being poor have any causal connection to having high IQ or not? Having the right kind of color of your face, does it have any causal connection to having high IQ or not? This is the kind of stuff, we don't even have any causal theory. We come up with fake causal theories, and our machines also come up with fake causal theories. But many other things we can actually do interventional experiments. Okay? So keep that in mind that when I say cause, actually I mean correlation. And sometimes I happen to know the causality, so I put that line here. In these kind of examples, I happen to know causality. Did I confuse everybody? Okay. Now, so I have decided a new theory. This is basically what I decided. Clouds, dependent on SP, sprinklers, then rain, then wet grass. This is my new theory. It's my theory. Okay, I mean, if you didn't mind me having this happy theory, you should certainly not mind me having that theory. The question is, how many numbers do I need for this? 1, 2, 2, 2. You see what I'm saying? If you can do this, then you understood basically how to specify Bayes network. Okay? So that's only 7. By the way, that network, what is that? It has a special name. It's called a Markov chain. This is the other thing. Everything you learned about probabilities is essentially a special case of Bayes networks. Actually, Bayes networks, and there is other thing called Markov networks, which we won't talk about. But really, most of what you know are special cases of Bayes networks. So how many of you have heard of Markov chains? That's a Markov chain. Okay? How about this? Suppose I have a network like this. Okay, maybe I can have a network like this. Cloudy. Actually, yeah, this cannot be written here as easily. But suppose I have a network like this: A, B, C, D, E, F, G. That's a network. What network is that? So essentially, it's also a network. And you can write the numbers for that too. Okay? These kinds of networks are called HMMs. Hidden Markov models. The idea, one of the interesting questions here, is which of these variables are observable. That means you can actually you can sense the value of the variable in the real world. And which are unobservable. Okay? In cases, some variables, in many domains, some variables are not directly observable. But they will cause evidence that is observable, observations that are observable. But just because you can't observe something doesn't mean it doesn't exist. And I'm starting to sound like the crazies from Roswell, New Mexico. But so just because you cannot directly observe a variable doesn't mean that it doesn't exist. It's a hidden variable. What?
Black matter.
Black matter. Yeah, you don't even need to go all the way to black matter. In general, some values of the state would be harder to directly observe. Some other values of the state are directly observable. Okay? In things like what hidden Markov model tries to say is you are trying to really figure out the hidden state, but you will only get the observations, which is that CEG. In fact, the way hidden Markov models are actually written would be S0 to S1 to S2 to S3, etc. that is state 1 to state 2 to state 3, etc. And then each state gives an evidence variable. You see what I'm saying? And so this is basically hidden Markov model. So in the context of this particular network, I could, for example, argue that wet grass is, in fact, in this network, kind of everything is observable. But imagine you are a blind agent. Okay? Then you can't observe cloudy. Okay? But you can observe wet grass. And from the wet grass, then you can say maybe either the sprinkler is on or the rain is on, and those may have some correlations with everything is cloudy. Okay? So the point of this slide is to say, if you understand Bayes networks, you can essentially say everything is a special case. Okay? By the way, in particular, there is a general name for these kinds of things like HMM. They're called dynamic Bayes networks. Because the question is, in this network, there is no notion of time. It's all in one snapshot of the world. In a given snapshot of the world, is it cloudy? Are the sprinklers on? Is it raining? Is the grass wet? In the current state. Okay? But normally when you have states evolving, okay, when the states are evolving, then they're evolving in time. So that's where the word dynamic comes from. Whenever things are changing over time, you say dynamic. And so HMMs, Markov chains are typically examples of dynamic Bayes networks. You see what I'm saying? And it's unfortunate, but you guys know, you may have heard of things like recurrent neural networks. You don't know this, but you know the other thing. That is a dynamic neural network. It's catching the notion of time in the neural network. Okay? And not surprisingly, these things are all connected. Okay, we'll be talking about it in a minute. Okay, so, any questions on this stuff? Yes?
Can there be a cycle in the graph?
So cycle in the sense of what? It has to be a cyclic graph. It has to be a cyclic, it's a, a Bayes network is a DAG. Actually, the top textbook on Bayes networks, for not really meant for the faint of the heart, is by Daphne Koller. And our group's name is DAGs. Okay? Daphne Koller is actually left academia and is trying to make millions. I don't know why, but she has too good a brain to actually spend time making money. But no, that's not fun. But DAG is what a Bayes network is, directed acyclic. Which might make you wonder, what about undirected graphs for probability distributions? They do exist. Okay? We won't talk about them. So the undirected graphs for probability distribution are called Markov random fields. And they look like this. Etc. You guys see this? There are no arrows. How many of you heard of conditional random fields? Yeah, that's a conditional random field. It's a particular Markov random network. It's of a particular type. The only thing that makes something a Markov random network, a Markov random field, is that the edges are undirected. But the point that you have to hopefully understand is it's not that the edges are magical. It is the semantics you associate with the network that makes it have certain properties. Okay? And it turns out that the difference between Markov random fields and Bayes networks is the kinds of conditional probability, conditional independence assertions that they can capture. That's a pretty deep point, and I won't go into that too much Maybe I will go into it, a class from now, but not necessarily. Okay. But that's basically, there exist these kinds of networks too. Okay. But base networks are much easier to understand. Okay. So the next question is, I gave you the numbers now. You told me what numbers to have, and I gave you the numbers. I asked myself, I'm an expert on cloudiness, and I put these numbers. Probability is 0.5. Clearly, I'm in London when I wrote this. And probability of sprinkler given cloudy, and probability of rain given cloudy, probability of wet grass given sprinkler and rain. Remember, one of the last questions I asked at the end of the last class is, would the world go kaboom if I put wrong numbers there? No. It's just a different world. It may not be your world. This is not Phoenix for sure, right? Because in what world is Phoenix going to have 50% chance of rain, except like today? It's 100%, but starting 3 o'clock, the rain just keeps going up. So I may actually not be going to Taiwan. I might be floating about somewhere here. But so here is my network. Okay, I asked myself as an expert and found these numbers. I want to know this probability. And remember, the joint probability distribution will have entries of this type. There will be exactly 16 entries of this type. Okay, and I told you how to do this. Let's go over it. Let's tell me how to do this. How do I get this number? So I start with, where do I start? How do I start? Topological started way. So start with cloudy. So cloudy, I want it to be true. According to my numbers, it's 0.5. Then I want sprinkler to be false. But it's in the topological sort. So not sprinkler given cloudy. So then I know sprinkler given cloudy is 0.1. Not sprinkler given cloudy is 1 minus 0.1. Right? So that's nothing but it's coming, that number is coming from here. Now I need to get rain. So rain, in essence, given not sprinkler and not cloudy. Except we know that rain only depends on cloudy. That's the whole point of the network. The network says, once I give the immediate parents, then in the topological sort, if I give the immediate parents, I'm independent of the ancestors. Okay, so in this particular case, I want rain true, given cloudy true, that's just 0.8, right? And then the last one is not wet grass. So not wet grass has to depend on sprinkler and rain. In particular, it should depend on not sprinkler and rain, because that's what our evidence currently, up until now, that's what we have. So not sprinkler and rain is this entry.